Okay then, thank you. Thank you so much.
Okay, our next speaker is an invited speaker, Professor Ted Ralphs. I'm requesting Professor Ashutosh Mahajan to give an introduction.
All right. Professor Ted Ralphs is a faculty member in Industrial and Systems Engineering at Lehigh University. His research interests are mathematical optimization, especially the computational aspects of optimization. He's one of the co-founders of CoinOR, which is a public repository for very nice software for optimization. So if you have any optimization problems to solve and you are looking for open source software, CoinOR is the place to go. I think he's all set, and I think we are running a little ahead of time, but I think he has enough material to take up all the time, and even beyond if need be.
Thank you very much. And thank you for accepting our invitation to be here.
Okay, thank you. And thanks to the organizers for the invitation, and for ASHU for organizing this visit. It's been great. I've been in India for more than 2 weeks now, so gotten a little bit acclimatized. This is going to be a kind of very quick, I'm going to go through a lot of things very quickly, building on some of what ASHU said yesterday. I have a lot of slides, and I'm going to flip through them quicker than maybe you can absorb them, but I want to give you a kind of overall viewpoint of what you can do with these tools, and then I'll make the slides available if you want to look at details. But I wanted to have everything there for you to look at later. So I'm going to actually introduce another system besides Pyomo that ASHU introduced yesterday. But I want to kind of first give you a quick overview of kind of the ecosystem that these things exist in. So the way that these languages are designed is kind of a lot of, has evolved out of kind of a history of how people, of the workflows that people use for doing this kind of analysis. So ASHU kind of explained yesterday that the modeling language is separate from the solver. There's actually kind of 4 steps that we usually follow in doing this kind of analysis. So first develop what we call an abstract model. So it's not really you have the data, but just what is the model that we want to develop. Then populating the model with data as a separate step. Solving the model, which is again done by usually another piece of software, and doing some analysis. So there's potentially 4 pieces of software or even more that are being integrated here. And so that I'm going to talk about the modeling step, but again, this is sort of separate from the software that's being used there is separate from the software that's being used for the other steps. And what is kind of ideal about Python is that it provides kind of a way of binding all these things together fairly seamlessly. So I'm going to talk about CoinOR. ASHU introduced CoinOR a little bit. I just wanted to say a few words. We are a nonprofit foundation, and we do, a fair amount of things such as supporting the development of the kinds of solvers that you see here. We also develop standards and maintain standards for interchange. So a lot of the ecosystem only works because we have common interchange formats for data between the various tools in the stack, and we work on those kinds of things. And then we run a repository which is available to developers that want to develop software for operations research applications. I'm going to talk about the stuff I'm going to talk about is dependent on what's called the CoinOR optimization suite. This is a subset of all the tools that are in the repository, but kind of bundled together in a nice way. And it includes solvers for most of the common classes of optimization problems that you see in practice. So the things that Ashu kind of introduced yesterday. I just wanted to make it clear that, in fact, this stuff is pretty easy to use on all operating systems. Whether you're on OS X, Windows, or Linux, there's pretty easy solutions. I'm not going to go over the details of it all here for lack of time, but I have a tutorial that I gave that consists of 5 lectures, like how to do all this stuff in a fair amount of detail, and the URL is there, so you can find out how to install Coin for your operating system there in detail. But the high-level summary is, there's a GUI installer for Windows, which you can get at the URL there. There are homebrew recipes for most of the projects on OS X, and we're working on getting more of those. I have pull requests open as we speak to get those recipes into homebrew. And on Linux, everything works from source very well. So downloading the source and building should be no problem with the standard auto tools kind of configure, make, install. Okay. Now, as far as the modeling language ecosystem, there are some big commercial players in the U.S. That, as Ashu explained yesterday, have their own kind of programming language built into the modeling system that you have to learn. The advantage of the Python-based languages is that they're built on a language that we already know, so it makes the barriers to entry pretty low. And there are actually 4 Python-based modeling systems in Coin. I'm just going to talk about 2 of them today, but the other 2 are also there and allow more low-level kind of access. There are many other front ends that allow you to use Coin. Most of these are commercial, but there's an R front end. Coin is actually now the solver embedded in OpenOffice, and you can use it from these other systems. I'm going to talk about 1 or 2 of them a little bit later. Just to briefly tell you how the exchange of data happens under the hood. So there are some common formats, and actually the 2 systems that I'm going to talk about today communicate with the solver through file-based I/O, so that's a little bit not so ideal, but there's a lot of reasons why that's kind of the standard way that it's done. So there are some common formats for passing the data, but there are also some projects that use C extensions, so I have one that uses C extensions, and you can get the data in directly through memory. Okay, so that's kind of a brief overview of the ecosystem, and now I just want to go into some examples and show you what you can do with this stuff. Again, I'm not going to dwell on the details too much, but so Pulp is something similar to what Pyomo, to the Pyomo system that Ashu introduced yesterday, but it's a little bit more Pythonic, a little bit easier to work with, but it only does linear modeling. I want to show it to you just because it is kind of a little bit, if you have a linear model, it's a little bit easier to work with, and it creates models that are much more human readable. So this is something like, the basic kind of model that Ashu showed yesterday. We have some variables, and we just are creating a simple model that says here, I want to maximize the function 4 times x1 plus 3 times x2, subject to these linear constraints that you see there. So in Pulp, we can just create variables. They're Python objects, and then I can add the expressions representing the constraints just directly into the model using, the plus equals operator. So it's all kind of, to me, it's very Pythonic, as a Pyomo is a little less so. Now, what we really want to do is develop, what I call an abstract model, where instead of specifying individual variables one by one, we have a model that says, kind of at a more high level what we're doing. So this is a lot of examples I'm going to show you are from the finance world, because I just taught a course in financial optimization. So this is a very simple bond portfolio model, and actually it's probably easier to explain it if I just show you the input data. So we have the input data is we have some bonds which have properties such as their yield, their rating, maturity, and so on. The model that I'm showing you on the previous slide is just to maximize the average yield of our bonds, subject to some conditions such as that the rating should be, no more than a certain average level, and the maturity should be no more than a certain average level. So when we build the abstract model, we can actually we can declare sets of variables that are indexed. And the way that the indexing is done is just like a Python dictionary. So we have what's called a variable dictionary. And so you can see where it's declared there, the variable dictionary is indexed on the keys of the bonds dictionary, which is the input file there. So my list of bonds is going to be the keys in this dictionary. So A and B are the bonds, and I'm creating an indexed set of variables on that list. Okay. Oops. And then the constraints now I can build constraints using comprehensions in Python, and so I have my first constraint there is basically saying I'm going to optimize the sum of the yield times the amount of each bond that I'm going to buy. So that's my objective function, and then the other constraints are the ones that I showed you before, saying that the average of the maturity and the rating should be at most a certain maximum level. So the LP sum function here is just taking a summation of variables multiplied by coefficients. But the whole thing kind of reads very much like a mathematical model that you would write in mathematical notation. So it's very pleasing in that sense and very easy to work with. Okay. I think I already said most of that. Again, I'm skipping over some of this stuff, but if you want the slides, you'll be able to get them afterwards. And then when I want to print out the solution, I can access the variable values just in the way you would expect. So I have that dictionary of variables by, and I just take the individual variables in that dictionary and access their value after the solution with the var value property attribute. Okay, I'm going to skip over this example and get on to something a little bit more complex. So this is what's it called, a combinatorial model, where I have variables that represent yes/no decisions. So this is what's called facility location. I have some candidate locations where I want to put facilities. I have some customers, and what I want to do is choose where to put the facilities and then assign customers to a facility subject to some capacity constraints. So I can assign, at most, so each customer has a level of demand, and a facility can service at most a certain total demand. So my variables correspond to which facilities to open. So I have one variable per facility, and that's going to be a 0, 1 variable, depending on whether the facility is open or not. And then I have variables that tell me whether a particular customer is assigned to a particular facility. My constraints then here in mathematical notation, the first constraint basically just says I can only assign each customer to exactly one facility. And then the second set of constraints there says, are the capacity constraints that says the total demand assigned to a facility can't be more than the capacity. The third set is just saying I can't assign a customer to a facility that's not open. And finally, then I have the binary restrictions there. So, and this can all be done, very compactly in pulp. And here, what I'm doing is, whoops. So this is just a little bit higher level type of model here, where I have actually now not only indexed sets of variables, but I have indexed sets of constraints as well. So I have loops where I'm adding constraints that are indexed. If you look at the original model, here I have each of these lines of each of these constraints is a set that's indexed. So I have one type of the first constraint per customer and one type of the second constraint per location, and so on. So I can just create a loop and add those constraints one by one, and basically in the same way that I showed you earlier. Okay, and this is just the input data, just showing you how that would be done. Okay, now, so moving on to Pyomo. Again, Pyomo adds the ability to have nonlinear constraints, and with that comes the fact that it's a little bit heavier weight and a little bit harder to understand some of the concepts. But this is what you need. This is the kind of power you need if you want to do the nonlinear modeling. Okay, so this is just, again, this is another simple financial optimization model. It's called portfolio dedication. Basically, I want to construct a portfolio of bonds that's going to offset some liabilities that I have coming in the future. So I want to buy some bonds now that'll cover those liabilities. So the constraints here, this is a lot of notation, but basically the first constraint just says, there's a cash flow constraint that cash in equals cash out. And the second set of constraints is just a different version of the first constraint for the last period. And that's basically it. So I just have to make sure that my cash flows are balanced. And so I can write this in pulp. Now I'm going to sort of contrast pulp with Pyomo. So in pulp, this is how you would write it. I mean, it looks like a lot of stuff, but it's basically just that, one equation just saying cash cash out in every period. Now in Pyomo, well, I should mention that, well, there's a little bit, so the data for this example is actually stored in a format which is not a Python-based format. It's a format which is used with the AMPLE modeling system, but since AMPLE is such a commonly used system in the US, that's become kind of its own standard. So I actually have a Python function here which is parsing that. Now what Pyomo provides is the ability to automatically parse all kinds of data formats, including the AMPLE format, and that's one of the more powerful things about it. This is the Pyomo model for the same thing, and it actually looks almost the same, except that we have to put the action for the constraint inside a function now. So it's almost exactly the same model. Now, one of the things that Pyomo allows you to do, well, all right, let me just quickly, this is just stuff that Ashley talked about yesterday, but so once I have that model, one of the ways to solve it is on the command line. I can just invoke Pyomo on the command line, read the script in. But of course, the way that, to me, the way that you would obviously want to do this, because you're only using Python in order to embed this in some bigger application, is that you would want to, do it within a script. So it's not that much harder. You just need to get an object from the solver factory corresponding to the solver that you want to use, and then I can just create my instance and solve it, and then get the results out. So you see here that getting the results is pretty much the same way that it is in Pulp. Now the difference with Pyomo is that Pyomo has a notion of an abstract model which is then populated with data when you call the create method here. So until you call that create method, the model is just an abstraction. The create method actually puts the data in and makes what's called an instance. Then it's the instance that actually gets passed to the solver and is solved, and then the instance is where the results are contained. So this is a little bit of this again comes from the way that modeling languages typically have worked historically. And just to quickly show you, you can actually create a whole model in Pyomo without having the data present, as opposed to Pulp, where you have to actually have the data in order to create the model, because the data, you're actually creating the instance right there in the Python. Here you can create things which are basically, it's an abstraction which says, I'm going to have a set of that I'm going to give you later, but I don't know what they are right now, so I'm just going to create this placeholder which I can then index other things off of and so on. All right, and that's what the abstract model looks like. Okay. All right, so those are kind of the basics of Pulp and Pyomo. So now I want to show you one very useful tool, which is a Spreadsheet plugin. I'm going to kind of show you some more advanced examples now of how to use these things. Solver Studio is a Spreadsheet plugin which works with Excel. Unfortunately, I am using one piece of proprietary software here. But my reason for showing you this is both because it's very cool and useful, and because I'm looking for someone to do the same thing in OpenOffice. So if you want a nice little project to do, I think what I'm going to show you should work in OpenOffice. but it doesn't at the moment. So, all right. So this is Solver Studio now. Oh, whoops! I forgot that it's not. Okay, yeah, this is going to be a bit of a challenge because I can't see. Oh, and it's also. All right. So this is Solver Studio. What Solver Studio allows you to do is actually write Python in the spreadsheet. So your Python editor is in the spreadsheet, and you can pull data from the spreadsheet into Python. So you can populate your model from the spreadsheet, and then you can export the data back again. So this is a very, I think this is very cool. It's also extremely useful for working with students because it gives them a way of just quickly getting data into a model. And they're used to spreadsheets. At least our students are happy to use spreadsheets. And so this is, what this is showing here is again, another little generalization of the bond model that I showed you earlier, where now I can have an arbitrary set of properties of bonds that I want to constrain, and I can actually change which one is being optimized and which one is being constrained, and even create trade-off curves. So here I'm creating a trade-off curve of, as I vary the rating constraint and optimize the yield, what does the trade-off look like? And I'm doing this by over here on the spreadsheet. Whoops. Over here, I'm looping and basically building a bunch of different models and running them all, and then populating the results back into the spreadsheet. So I can run this thing, and, well, the data's already been in there from a previous solve, but what I just did there was solve and create this trade-off curve here. Now, the way that you get the data across is by, you have a dialog, which of course appears on the other screen. This dialog basically creates the mapping from the spreadsheet cells into the Python variables. So I can say which range of cells parse to which variable in my Python model. There's also some nice features. I can highlight the data. This actually creates an overlay. It shows me which ranges correspond to which things in my model, so I can see, more easily kind of what's going on here. All right, so very cool stuff, I think. So that's Solver Studio. I'm going to show you another example in a little bit in Solver Studio, but so that was one that I just showed you, and there's a screenshot in case I couldn't get Excel to work. And, okay, now I have, the rest of the talk is a bunch of more involved examples, and I'm not going to have time to go through all of them, but these will be, again, available. The slides will be available to you. So I just want to kind of do two more in the time that I have left, and that should get us right to the end. So I just showed you the trade-off analysis. That was trading off two different objectives against each other. I'm going to show you one nonlinear example here, and this is portfolio optimization. Again, the finance theme. But what this example is showing is a simple model for selecting stocks or investments. So we have two inputs here. We have some data about returns over time for various stocks, and then we have some data about their variability. So the variability is kind of the risk associated with the stock. So the more variance, the more variability there is in the here that investment is. So the basic portfolio model that is used in industry, well, I mean, if they use things a bit more sophisticated than this, but basically we're maximizing the return subject to some risk bound. So we don't want the risk to be more than a certain level. And of course, this is also something we can trade off. So we can trade risk and return and create curves just like I showed you before, and that's what I'm going to show you again here. So let me go back to where did my cursor go? There it is. Okay, so this is the portfolio optimization model in a spreadsheet. So I have some stocks across the top there, and I have their returns by year, and the model is over here. Now, what's really cool about using Python to do modeling is that I can integrate my data acquisition into the model. So what you see up there is basically a few lines of code that goes out to Finance and actually populates the spreadsheet with data from Yahoo Finance. So in principle, you could do some sort of live updating of this stuff. I'm not going to try to fetch the data live here, but this data was actually fetched from the internet using Python. Very, very cool. And then what I'm doing is solving a bunch of these portfolio models at different risk levels and looking at what the return is going to be. So that's creating my risk return curve there. So if I run this, then you'll see that it's going to run. Now this is using IPOP because we have a nonlinear model here, and it's solving each one of these portfolio models and then populating the returns here and creating that trade-off curve. So all done in a spreadsheet with Python. Very, very cool. All right, I have one more kind of gee whiz example. If I can. Okay, so this is Eclipse, which is what I use often for doing my Python coding and debugging. So what this is what's called the traveling salesman problem. Many of you have probably heard of it. It's one of the most well-known optimization problems. Many people have worked on it. So this is a problem to find the shortest way of visiting a list of cities and then returning back to where you started again. So this is what this little Python script does is, again, goes out, fetches data from Google Maps to create a distance matrix of the distances between various locations, with the real driving time, and then calculates the optimal and then shows it back on a Google map. And I'm not going to try to do this live either. Well, I can actually run the script itself. That should not be a problem, but so it went out. So if this were, well, don't copy my Google key there. It's there's some code here which goes out and fetches the data. That's this little function. This is the model itself. Now there's, with the TSP, for reasons that I can't really explain in a short amount of time, we can't just create a very compact model. We have to actually derive the model iteratively. So there's some functions here that I need to define that are part of the modeling environment. That this is a modeling system that I'm not really showing you, but just to give you an idea of what's possible. There's a few functions that I have to create, and then here's my solve call. And then what's at the bottom here is just the HTML that creates the map and puts the optimal solution back on the map again. And if I can do it, I'll try to show you then the well, this is too large here. Let's see. Oops. Okay, so this is the result. So, if I have an internet connection and everything were working well, then I could do this, live. But this is just, again, another kind of GWiz example of what you can do with the Python tools when you integrate these solvers into the Python ecosystem. So very, very neat stuff. And with that, see if I can fix that. Well, I had somewhere in here I have a slide that I wanted to show last. But maybe I'm not going to be able to find it. Here we go. Okay. Thank you very much. I'll take questions.
Thank you very much. Do we have any questions? Time for questions.
Oh, yes. So, yes, many of them are on the GitHub website, or my GitHub site. And, yeah, most of them are on GitHub. So, yes.
Any more questions? All right. So if there are no more questions, we thank the speaker again. Thank you very much. Thanks again.